My name is Burri Anil. I am from Hyderabad. I completed integrated MSc Chemistry from Usman University. I have 2 years of experience as a NEET chemistry faculty in nearby Foundational Institute. Okay. Today I am presenting a demo topic which is from inorganic chemistry, which is coordination compounds. Right. So coordination compounds. So before this, I like to explain the what are addition compounds. When two simple compounds add during crystallization, we get a crystal compound that is called addition compound. If addition compounds are subdivided into two types. First one is double salt and second one is coordination compound. So addition compounds are subdivided into two types. First one is double salt and second one is coordination compound. So what are double salts? When we mix two different salts in two different simple salts in a fixed stoichiometric ratio, and we get crystal compound that is called double salt. So for example, so we can say, we know that potash alum, more salt, so carnallite. So there are different double salt. For example, potash alum, K2SO4, Al2SO4, taken 3, 24, H2. So this is double salt. So what is coordination compound? So in this, a ligand which donates its pair of electron to vacant d orbitals of metals, and it forms a coordinate bond. The bond formed between metal and ligand is coordinate bond, and the compound is called coordination compound. That is, for example, K4 FeCN taken 6. So this is the coordination compound and this is the coordination sphere. So this is the coordination sphere. So now what is the difference between double salt and coordination compound? Okay, so if I dissolve this compound in water, it dissociates into 2K plus ion, SO4 2 minus, and 2Al 3 plus, and 3SO4 2 minus. So, and this, if I dissolve this compound, coordination compound, in water, we get 4K plus FeCN6 4 minus. So it means when we dissolve double salt in water, total compound dissociate into individual ions, right? So here, if I dissolve this coordination compound in water, we get 4K plus and FeCN taken 6 4 minus. It means this is a coordination compound. It doesn't undergo dissociation in water. So this is the property of this is the difference between double salt and coordination compound. It means when we dissolve this coordination compound in water, it retains a property. It doesn't undergo cyanidation. But when we dissolve this double salt in water, it completely dissociates into ions. So that is the difference between double salt and coordination compound. Okay. So now I am explaining the different types of complexes. Generally, complexes are divided into three types based on charge distribution. Okay. So first one is cationic complexes. Second one is neutral complexes. Third one is anionic complexes. Okay, so what is cationic complexes? If charge is present on the coordination, if positive charge is present on the coordination sphere, that is called cationic complexes. If there is no charge present on the coordination sphere, that is called neutral complexes. If there is negative charge present on the coordination sphere, that is called anionic complexes. So for example, if I take CO NH3 taken 6 3 plus, CO NH3 taken 6 3 plus. So if you observe here, positive charge 3 plus is present on the coordination sphere, so it is called cationic complexes. So for example, Fe H2O taken 6. So if you observe here, there is no charge present on the complex, so it is called neutral complexes. What is anionic complexes? If negative charge present on the complex, that is called anionic complex. So this is the difference between cationic, neutral and anionic complexes. Okay, so now I am explaining the classification of ligands. So generally ligands are classified into 3 types based on charge present on the ligand and based on denticity, and the third one is like based on type of donation of lone pair. Okay, so first one is based on charge. It means ligand is again subdivided into 3 types. First one is negatively charged ligand. Second one is neutral ligand. Third one is positively charged ligand. So it means these are, what is negatively charged ligand? If the ligand having negative charge, that is called negatively charged ligand. For example, Cl minus, fluorine minus, Cn minus, SO4 2 minus, etc. So these are the negatively charged ligands. What are neutral ligands? For example, H2O, NH3, etc. So these are the neutral ligands. What is positively charged ligand? For example, NH3, NH2, positive. So hydrogen ion, and another one is NO plus, etc. So these are the negatively charged ligand. If negative charge present on the ligand, that is called negative ligand. If there is no charge, that is neutral charge, that is called neutral ligand. And if positive charge present on the ligand, that is called positively charged ligand. And now another one, second type is based on the denticity. Okay, so based on density, what is density? What is density? Number of types of donation of lone pair to the metal atom, that is called denticity, that is subdivided into, first one is monodentate ligand, second one is bidentate, third one is polydentate, and another one is ambidentate. So what is monodentate ligand? If ligand is coordinated with one atom to the metal atom with one pair of electrons, okay? For example, if I take H2, NH3, so here denticity is 1. It means one atom donates its pair of electron to the vacant d orbitals of metal. It means here oxygen is donated to the metal. So its denticity is 1. So that is called monodentate ligand. What is bidentate ligand? In one ligand there are two donor atoms. Okay. For example, ethylene diamine. Okay. If I take ethylene diamine, CH2, CH2, NH3, NH3. This is ethylene diamine. It is one ligand, but there is two donor sites. It means in one ligand there are two donor sites to donate to the metal atom. So it is called bidentate ligand. Okay. What is polydentate ligand? In one ligand there are n number of donor sites. Okay. For example, EDTA. Ethylene diamine tetraester. So it has 6 donor sites. So in one ligand there are 6 donor sites. So this is called polydentate ligand. What is ambidentate ligand? So in one ligand there are 2 donor sites are available, but simultaneously it donates only one pair of electron to the metal atom. For example, SCl, etc. So sometimes S will donate pair of electron to metal, and sometimes nitrogen will donate pair of electron to the metal. So this is called ambidentate ligand. And last one is based on type of donation of lone pair. Based on lone pair donation, it again subdivided into 3 types. First one is sigma donor, second one is sigma donor pi acceptor, and last one is pi donor pi acceptor. Okay. So if the ligand donates its pair of sigma electrons to the metal, that is called sigma donation, we can say NH3. A pair of electrons donate its sigma electrons donates to the metal atom. So it is called sigma donation. So and another one example is, and another one type is sigma donation and pi acceptor. It means if you check in CO, it can donate its pair of electrons to this metal, that is sigma donation, and parallelly it can accept electrons from the metal. So that is called pi acceptor. And another one is pi donor and pi acceptor. That is ethylene. So it can donate pi electron to the metal, and also it has vacant pi star orbitals. It can take electrons from the metal. So that is called pi donation, pi acceptor. So this is the concept which I am explaining. Now I am explaining the problems. Okay. So first question is, so the geometry and magnetic behavior of nickel CO4. This is the example which I can take. Options is square planar geometry, and paramagnetic, and second one is tetrahedral and diamagnetic. I am writing as dia. And third one is square planar and diamagnetic. And last one is tetrahedral paramagnetic. So now here the question is, what is the geometry involved in this complex, and also its magnetic behavior. So first, before that, nickel is having 3d8 4s2 configuration. Okay, so if I write ground state orbital configuration, for a ground state orbital configuration, it has 8 electrons and 4s2 configuration, 3d8 4s2. Okay, so when ligand comes near to the metal, its excited configuration becomes so this is 3d orbitals, this is 4s orbital, and this is 4p orbital. Okay, so total how many electrons? 1 d8 is total 10 electrons. This 10 electrons becomes paired. Why? Because CO is a strong field ligand. So when CO is coordinated to nickel atom, so all electrons gets paired. So there is only vacant 4s orbital and 3 4p orbitals. These 1 4s orbital and 3 4p orbitals becomes hybridized to form sp3 hybridization. Means 4 ligands donates its pair of electron to these all orbitals, and it becomes sp3 hybridization. If we say it is a sp3 hybridization, it becomes tetrahedral geometry. So if you check in all electron distribution in orbitals, there is no unpaired electrons. So all orbitals are fully occupied. It means it is a diamagnetic in nature. Okay, so this how we can explain this example.